So very good afternoon to all of you. We were talking about noise in last few classes. We will continue to talk about it. In today's class, we are going to talk about the flow noise, noise due to motor vehicle, and some of the problems. With this, we will finish this chapter. As I had suggested earlier that we are towards the end of the syllabus. Chapters are small and they are going to finish very quickly. So starting with the flow noise, as the name suggests, it is noise due to the flow of a fluid and its interaction with its surrounding. The fluid noise can be classified into, or the flow noise can be classified into monopole, dipole, and quadrupole sources. A monopole sources look something like this. It is an interaction of a stream, flow stream, fluid or air, liquid, whatever, with a moving disc at a regular interval, like a siren. So when the flow of air is interrupted at a regular rate, then we get a monopole source of noise or sound. Example, a siren. In fact, somebody has done this project also, whereby he has made a disc which was made to rotate at a certain speed, and he could blow the air in the holes which has been crafted in the disc to produce the siren sound. Now here the sound pressure level is proportional to the fourth power of the velocity. So you can see that it is very sensitive to the velocity. If the velocity doubles, then the power output, the sound power output gets proportional to the fourth power. So it increases by 16 times. So that is one example of the flow noise. Other example of the flow noise is the dipole noise, generally called as where a where a stream or a fluid interacts with a metal or solid surface. If it's sharp, mostly metal, so solid object. Examples are many. For example, noise of air blowing through a grill, the sound generated by a moving fan. So your ceiling fan, if you turn on and turn off, you will find that it gives a big amount of noise. So that is the noise that is generated over here. Then aerodynamic whistles, etc. A lot of examples of this. So where the stream interacts with the solid object at a slow rate and gives flow noise. The sound pressure here generated is proportional to sixth power of velocity. So again, very sensitive to the velocity. That is why if you keep the fan at a low speed, you will find that the sound level reduces drastically. Okay, the third kind of noise is a quadruple noise. In a quadruple noise, typically the sound or the fluid is exhausted through a very narrow nozzle. One of the example that I can take, although it's not a very accurate example, this talks about a very high speed fluid, but if you take a large balloon and inflate it and then leave its mouth open, you will find that the air escapes through the large balloon at a very high speed, giving some sort of sound. So that is another example of this kind of source. This kind of sources are there in jet engines, any high powerful machinery, etc. So here the sound is generated basically because the, the gas comes out at such a high speed that there is a lot of turbulence or turbulent mixing, and that is why it gives a lot of sound. Noise from the gas jet in a jet engine is an example. Here the sound pressure is proportional to the eighth power of the velocity. So you can see that the velocity get doubled, the sound pressure increases 2 to the power 8 times. That is 256 times. So it's enormously sensitive. Most of the flow noise can be minimized. You can see that it is so much sensitive to the velocity that we should always have a velocity, fluid velocity flow at low velocities. High velocity of fluid flow will always give you very high noise. So most of the flow noise can be minimized by using a low velocity flow. That is why air conditioners are a better substitute for the fans, because as far as noise is concerned, low noise fans can be installed. There are limit by which the fans can have less noise. We will discuss that as well. But noise in the fan happens because of the reasons like rotating noise, rotating parts, machines, motor, etc. And aerodynamic noise, as we have already discussed, when the blade interacts with the air, it creates swirls or vortices in the air, which leads to the noise which is called aerodynamic noise. So the fans pose two kinds of noise in all the machines. And both of these noises can be amplified because of the resonances. Not on all frequencies, but maybe in some of the frequencies. For example, if you have if you have the fan blade moving, and if you have the body of the fan, if it is under resonance with the same frequency, then it will produce more noise. Or the surface on which the fan is mounted, if that surface has some resonant frequency, then again it will give to the same vibrations. Similarly, the the noise that the fan is producing, the aerodynamic noise, can get trapped into some parts of your room, home, where the air column can vibrate with the resonance with the fan noise. And then also it can get amplified. So both rotation noise and aerodynamic noise created by rotating fans can get amplified by resonances of various types. So one has to be generally careful when you are designing these systems. There are two types of fans we normally use. One is axial fans, which are very common. Our ceiling fan is an axial fan. A table fan is an axial fan. So this is an example of an axial fan. This is the axis. There are blades which are connected in radial manner. The blades are always slightly tilted. As they move, they cut the air, they push the air behind or in front at a certain speed, depending which is decided by the speed of rotation. It actually swirls the air in circles in the front, and that gives noise. They're typically noisier at all the frequencies, the ceiling fans and all. The other type of fan we normally get is called a centrifugal force or centrifugal fans, sorry. The centrifugal fan are like this. They have slight small blades at the periphery and they rotate this way. So when they rotate this way, they actually generate outward flowing momentum in the air from the center. So air is sucked from this hole, flows radially outward by using this device as a centrifuge, and then in the outer tube the air is directed and then finally comes out from this vent. So that's a centrifugal fan. This the image I've shown over here is a industrial centrifugal fan, but there are many very nice looking tabletop centrifugal fans which are also available in the market, which people use for their study tables, etc., etc. These are noisier at lower frequencies, but at higher frequencies their noise level reduces considerably. Lower frequency noise is generally a pleasant, or I won't say pleasant, I would say more pleasant or more bearable compared to a high frequency noise. And therefore, people sometimes prefer this. Noise due to motor vehicle, that is another example. Those of you stay near to an open road, highways, junctions, etc., they are exposed to this kind of noise. If your home is nearby to any of these places, then you are well aware of noise due to motor vehicles. Apart from the motor vehicle noise, there could be noise due to airplanes flowing overhead of your homes. If you are staying close to an airport, then there you will get a lot of noise. If you are staying next to a railway track, your building, your home is close to a railway track, then the train or metro station or whatever, then you will experience lot of noise. The discussion on airplane noise and train noise, I'm leaving it as a self study. There's a small and beautiful discussion in the book, so please go through that. I will discuss the noise due to motor vehicle here in this class. So let's have a look at this scene, which is a very common in our country. And look at how much noisy it can be. So you could see, wow, so noisy it was. And these kind of scenes are very common. Even in Bombay, there are many junctions, many places where the noise levels are enormous. And there is, so let us examine what are the sources of noise, motor vehicle noise, and how can they be controlled, reduced, etc. So one of the most noise source or biggest noise source in a motor vehicle is engine noise. Remember, the engines work on cycles, Otto cycle, diesel cycle, Rankine cycle, etc. And the combustion of fuel, every time it happens, if you remember from the basic theory, the fuel burns and undergoes huge expansion at a very small time. That actually generates lot of noise. In fact, it's a very, very loud noise. So it could be unbearable if it happens in opens. Fortunately, it is deeply buried inside the engine. It's a very small, it happens in a very small tube fitted with a piston, and it has a very thick engine metal cover surrounding it. So most of this noise is attenuated. Only some part of this noise goes out or get related to the exhaust. Then every time the cycle repeats, you get suction of air at some intervals, and at some interval you get exhausts of air. At both the time, the noise is created because of the pressure difference between inside the engine and outside the surrounding. Engine needs to be cooled at certain temperatures all the time. So it employs cooling fans, and the cooling fans do produce noise. Apart from this, the engine can transmit some of the vibrations if it is not properly insulated or damped, or if the damping system is has got corroded with time, then the engine may transmit some of its vibration to the car body, which can generate noise. So these are the various sources of engine noise in a car. The other type of noise in a car is aerodynamic noise. As we have discussed, when a vehicle moves, then the air mass interacts with the body of the vehicle, and as both the masses interact, then the sound is created. As we have discussed earlier, noise is created. Both both of these, engine noise and aerodynamic noise, are low at lower speeds, but as the speed increases, both of them becomes dominant. Modern day engines are fairly less noisy, and aerodynamic design ensures that aerodynamic noise is also minimal. A third type of noise which starts increasing with the speed is the tire noise. So as the tire moves on the road, the tire rubs on the road at some high pressure, and because of that rubbing on the road at the high pressure, especially at high speed, the So the tire noise is one of the reasons of noise at high frequencies. If you are living close to a highways, etc., where the vehicles are moving at high speed, you will hear a constant background sound. That is the tire noise. Finally, horns. Most of the vehicles are fitted with horns, and horns, as they sound, they are horns. They are designed to pinch. They are designed to make people alert, and therefore they are noisy. Lot of vehicles means lot of horns available, and lot of people honking means lot of noise production. Of course, that depends on this how much space is available on the road, what is the driving discipline, etc., etc., which actually not a very technical problem, but they are the social problems as well. But yeah, on an average, these are the four major source of noises on the street. So if any plan, any idea that uses or that tends to reduce the street noise must deal with reducing the noise in all four sections. Bad maintenance of the car generally will make all the noises go up, so the good maintenance is important. And one of the chief sources of noise, the exhaust system must have mufflers or sound attenuators. If those mufflers are not working, then again the lot of sound is generated or noise is generated from the exhaust. So you know that some of the vehicles make a lot of exhaust noise, and that actually is a trouble for other people. Poor training of driving. You know that the vehicles need gear change must happen at certain speed. You should not do clutch driving, you should not do honking, you should not do lane cutting, etc., etc. There are a number of rules that a driver must follow. If all the drivers follow all the rules, then most of the noise production can be reduced considerably. So the poor training to driver is also one of the reasons why you cannot reduce or eliminate noise. Most of the noise levels due to different cars, automobiles, trucks, and buses. Here is a simple graph. Typically, they fall in this category of 70 dB for cars. They fall in the category of 75 dB to 85 dB. 75 dB small cars, sports cars. If you have seen any sport event of the cars, then 85 dB, etc. Trucks are generally more noisier, starting at 85 dB and maybe ending at 95 dB. Buses, when they are moving in the city, they are moving at a less speed, so they make less noise. When they are moving on highways, they are moving at high speed, they make large noise. Now with this we come to the last section of today's lecture, and that is problems. Far more people are affected by truck noise than by airplane noise. Why are there fewer complaints, citizen protest groups, etc. directed against highway noise? So if you look at places where people are living next to the highways, at least I don't live far from the highway. I live around say 100 meter, 50 meter to 100 meter from the highway. That actually makes highway noise fairly less because there are tall buildings in the middle. But these tall buildings which are in the middle next to the highways, they actually are exposed to huge amount of highway noise all the time. But nobody apparently complains, nobody is protesting against it. Most of the time, I feel the answer lies in the ignorance. As a society, we don't care about pollution at all, be it air pollution, be it noise pollution. Highway brings both noise pollution as well as air pollution, and we are least bothered about both the kinds of pollution. In fact, if you look at a cursory check at the uh, prices of the homes in Mumbai city, you will find that if they are on the highway, they are more expensive than if they are little away from the highways. So therefore, you you will be surprised why, I mean, so much of noise is there, but nobody is protesting against it. Similarly, crackers and all, Diwali noise, they also create so much of pollution, both noise and air, but we hardly bother about them. How many watts of sound power and mechanical power are delivered by a typical automobile? So I think we have discussed this earlier. This comes from this graph. We have seen that a very small part of the total mechanical power is converted into the sound power. A typical automobile moving at 65 miles per hour, roughly around 90 kilometer per hour or something, it has around 10 power 4 watts of mechanical power, but it has only 10 power minus 2 watt of sound power. The sound power is minimal. So that is one thing. Find the lowest resonant frequencies of steel panel with dimensions 1.5, width, length 1.5, width 1, height 10 power minus 3 meter. Velocity of sound in steel is 4905 meter per second. So yeah, so lowest resonance frequency of the steel panel, you can have the formula. I think I have already put the formula earlier. I can put it again. So VLH M by L square plus N by W the whole square. So if you want lowest, you can go for say F10, or if you can take F1 and N as 0. So that will give you the lowest one. Then after that, you can go for 0 and 1. That will be the next one. And then you can go for 1, 1. So these are the lowest three frequencies. Yeah. So I think with this, we can stop discussion on this chapter. Thank you. I'm going to create a Google Meet for discussion. So anyone has any doubts, questions, clarification can come over in the Google Meet and talk.